Hey math fans, Alex here, and today we're going to continue talking about the expected value of a random variable x. So go ahead and recall that for a discrete random variable x, we had that the expected value was just the sum over all possible x of x times the probability that x was equal to x. Okay, so I'm going to go ahead and give you a claim now, and the claim is that for random variable x continuous, we have the following expression for the expected value. Just as you would expect, instead of an integral, or instead of a sum, it's going to be an integral over all possible x of x times the probability. Well, in this case, it would be the probability density function, so it would be that dx. Now, this is a claim, and it can be proved just from the discrete case using sequences of random variables, but I'm going to go ahead and omit the proof, which I don't usually do, just because it's going to distract from the overall idea. Okay, so one comment before we get into a practical example is the properties for continuous random variables derive from those in the discrete case. And what do I mean by properties? I should probably specify that. Okay, so maybe I'll put like a star right here. And what I mean by properties is what we derived in the last video. These fun ones, which I really don't know where to put them, but maybe I can make them smaller. Okay, so this is what I mean. So all of those also work for continuous variables, and that's pretty important because we're going to use those properties a lot. All right, let's move to an example. All right, so example 7, part A. Let x be uniformly distributed on A to B. We are to find the expected value. So I'm just going to remind you that the PDF looks like this, right? It's 1 over the length of the interval for x in that interval and 0 otherwise. Okay, so without actually doing a computation, let's see if we can come up with what we think the expected value is. So we have this continuous region from A to B. And yeah, we're not summing stuff up, but where would you expect the middle to be if every point in this interval is uniform, has the same probability? Each region here has the same probability of being selected. Well, you might expect that that's the expected value right in the middle. So let's see if that is actually the case. So remember that the expected value is going to be the integral over all x, okay, but in this case we can go ahead and just say x goes from minus infinity to positive infinity of x times the probability density function of x with respect to x. But the probability density function is 0 everywhere except the interval from A to B. So that makes this really easy. This is just the integral from x equals A to x equals B. That's the only way to get a non-zero value of x times whatever the PDF is, which is 1 over b minus a dx. Okay, so I can pull this 1 over b minus a out in front of the integral. Okay, and when I actually compute the integral, that's going to be 1 over b minus a times x squared over 2. And I'm evaluating from x equals a to x equals b. Okay. And then when I actually plug in the bounds, I get this factor of 2, right? This factor of 2 can just kind of come out. So it's going to be, let's put the factor of 2 right there. And then I get b squared minus a squared. Okay. But b squared minus a squared is a difference of squares, so that's going to equal b minus a times b plus a divided by 2 times b minus a. And you can see the cancellation here. And I'm going to swap the order of b and a to get exactly what we would expect, a plus b over 2, which is the midpoint of the interval from a to b. So everything kind of looks correct. All right. Now, little note on notation. Guess I can do that in this color. So the expected value, so we'll do this in black. So the expected value of x is sometimes called the mean of x, and is denoted with the Greek letter mu. And usually to distinguish it from other random variables, we put a subscript of the random variable. Okay. The reason that I'm defining it that way is because these are going to be interchangeable, and this is kind of a lot to write. Okay, so we're going to also define something called the mean square value of the random variable x, and that is going to be the quantity that is the expected value of x squared, and can be found with either, kind of discussed this in the previous episode, can either be found like that for x discrete, or now with the continuous case. The continuous case also says that if you have a function of x, right, you can just replace it in the integral, multiply that times the probability density function for x continuous. Okay. Now, probably one of the more important definitions. Okay, so we're going to define something called the variance. So the variance sometimes called the dispersion of a random variable x, which is going to be symbolized differently by different people. I'm going to choose to do var of x. And that is the mean square value of the quantity x minus the mean of x. Okay, so more specifically, we have that the variance of x, and you can take this as a definition. The variance of x is equal to the mean squared value of x minus the expected value of x. Okay, so we take this guy and then we square it, find the expected value of that. Okay. What on earth does that mean? Here's what it means. If I have a bunch of data, so if I have a bunch of data that's kind of all over the place, and maybe the probability is weighted, maybe these have a higher weight than these, and the expected value is somewhere over, I don't know, right here. That's my expected value. I want a measure of the spread. And the most basic idea of what spread is to take the biggest value minus the smallest value, and that's range. Well, that doesn't really tell us much because clearly I can have outliers, so it's not immune to outliers. However, one thing that you can do, the median is a little more user-friendly to outliers, But another measure of spread is something called the variance, which you basically take all these data values and find out the distance to the mean, and you square it. So squaring it is going to emphasize big numbers and small numbers. Okay, so big numbers, when you square them, become really big, and small numbers, when you square them, become really small. Okay, so after you add up all of those differences, the variance really tells you, on average, if all of the data is close to the mean, then you'll get a small number, or if they're really spread out all over the place. Okay, the classic example that I give students all the time is if you have a data set of temperatures of 0 degrees one day and 0 degrees the next day, and then if you have a separate measure, maybe it's minus 20 one day and 60 degrees the next day, I would trust the weather from this data set and not the weather from this data set. Even though the averages are one measure, the variances are quite different. Okay, so I'm going to go ahead and leave this as a claim because this is not an easy thing to calculate. Back in the day, when I took statistics, we had to compute these by hand, and I'm just not going to make you do that. So instead, we'll write this as a claim, perhaps. And the claim is that the variance of x is actually equal to the mean squared value of x minus the expected value of x. Okay, that was the worst x I've ever drawn in my life. I'll be ashamed later. All right, squared. Now, this is extremely useful for us because we know how to calculate this. We know how to calculate this, and it's a direct formula, and it's a lot more straightforward than trying to figure out what that is. But let's go ahead and prove the claim. This is kind of an important proof, I would say. So we're going to use the definition. So the variance of x, by definition, is the expected value of x minus mu sub x squared, okay, which we can go ahead and expand out, right? And just FOIL this out. So this is going to get us x squared minus 2x times mu sub x plus mu sub x squared. And then what we can do is we can go ahead and use the linearity of the expected value and write this as just the expected value of all these added together. I'm going to pull, by the way, I'm pulling this and this out because they're constants. The expected value of x is a constant. Okay. Okay, so it's that times the expected value of x plus mu sub x squared. Okay, but wait a minute, isn't mu sub x the same thing as the expected value of x? So everywhere I see that, I'm just going to go ahead and replace that. So this is minus 2 times the expected value of x times the expected value of x plus the expected value of x squared. Okay, and clearly this is going to be expected value of x squared and then minus 2 times the expected value of x squared plus 1 times the expected value of x squared. Okay, but these two are going to combine to give us what we want. Okay, so that's going to equal the expected value of, I'm just going to put parentheses here, minus the expected value of x quantity squared. So that's a very, very useful formula for finding the variance. You do not want to compute it the old-fashioned way, trust me. Let's move on to another example. All right, so example 7, part B now. Let x be uniformly distributed on A to B. I gave you the PDF again. And this time we want to find the variance of x. Okay, and just to remind you, the expected value of x was just the average of the endpoints. Okay, so how are we going to do that? Recall that variance, this magic formula, which you're going to write a bunch of times, is going to be the expected value of x squared minus the expected value of x squared. Well, we already know one of those things. We just need to find this. Okay, so let's do that. So the expected value of x squared is going to be the integral. We can go and skip the minus infinity to infinity. We know it's going to be from a to b of x squared times the probability density function. Okay, but then we're going to pull the same trick, right? Pull out the 1 over b minus a, go and integrate this. So it's going to be 1 over b minus a times, and then the integral of x squared is going to be x cubed over 3, evaluated from x equals a to x equals b. Okay, but when we do that, we're going to get, let's see, 1 over maybe 3 times b minus a times b cubed minus a cubed. If you'll recall the difference of cubes formula, that's just going to be b minus a times the quantity b squared plus ab plus a squared, all divided by 3b minus a. Not surprisingly, the b minus a's cancel, and I'm left with, I'm going to write it like this, a squared plus ab plus b squared, sure, all divided by 3. All right, so this really doesn't have a special name. I know I called it the mean squared, the mean square value or something like this, but really isn't too special other than to find the variance. So let's go ahead and find the variance now. So the variance, which was the expected value of x squared minus the expected value of x squared, that's going to be this a squared plus ab plus b squared all over 3 minus a plus b over 2 squared. Okay. Well, this is going to have a denominator of 4, and this has a denominator of 3. So I want everything to have a denominator of 12. All right, so this is going to be, let's see, 4 times a squared plus ab plus b squared minus, and then I want this to have a denominator of 12, so I need to multiply it by 3. And everything should have a denominator of 12. And then when I figure that out, that's going to be, 4a squared plus 4ab plus 4b squared minus 3 times a squared plus 2ab plus b squared all over 12, okay, which is going to be, let's see, a squared, right, because the 4a squared and the minus 3a squared are going to give you a 1a squared. 4ab minus 6ab gives you a minus 2ab. 4b squared minus 3b squared gets you a plus b squared. Which you can factor this, by the way. That's just a minus b quantity squared over 12. And that's the variance of the uniform continuous distribution. Whenever you find a new distribution, and trust me, there are going to be several, especially in the next chapter, you always want to find the mean and the variance of it first. Those are incredibly useful. All right? Okay. Now I just want to end off with one little application of expected value and variance. All right, so we're going to talk about something called Chebyshev's inequality, and there are a million ways of spelling his name, and it's almost like Hanukkah. But the book that I have is written by a Russian, and Chebyshev was a Russian. So I'm going to go ahead and trust that this is spelled possibly correctly. And the idea is, let's suppose that for some reason you want to know the probability that a random variable x has a magnitude that is greater than some epsilon, which we'll consider positive. Okay, so the idea is, okay, maybe this is 0, and maybe this is epsilon, so this is minus epsilon. So we want to know the probability that the random variable lies somewhere in this region. So we want to know either of those regions. Okay? So in general, we can't find this probability, or we can't find this exact probability without knowing what? Well, you got to know the distribution of your random variable. You got to know the PDF. Okay? But what we can do, we can bound the probability above. And that's going to be Chebyshev's inequality. Okay? So, here's the idea. What we want to do is we want to find the probability that the magnitude of x exceeds epsilon. Of course, if it's greater than or equal to doesn't really matter for the continuous case, but it absolutely matters for the discrete case for obvious reasons. So that's what we're wanting. Okay, so how are we going to do that? Well, the first thing that we're going to do is we're going to consider the random variable y. And I'm going to go and define that for you. It's going to be a piecewise function. We're going to go and let it be 0 if the magnitude of x is less than or equal to epsilon. And we're going to let it be epsilon squared if the magnitude of x is greater than epsilon. So kind of a weird random variable. But before I even say anything about the random variable, I want us to consider two cases. So I want us to note that if the magnitude of x is less than or equal to epsilon, then the random variable y is equal to 0. Okay? Which has to be less than or equal to x squared. Okay, because the square of a number is always non-negative. Which x squared has to be less than or equal to epsilon squared. If it's in this distribution, right? Y is equal to 0, then the absolute value of x has to be less than or equal to epsilon. Well, that implies that at x squared, which we've went ahead and said is greater than or equal to 0, that has to be less than or equal to epsilon squared. Okay? So the key part that I wanted you to get is this part. Right? Now, if we have that the absolute value of x is greater than epsilon, then what do we have? Well, then we have that x squared has to be bigger than epsilon squared. Okay? But epsilon squared is equal to y. Okay, so maybe it was a misnomer to highlight this, so let me just redo that. So All right, so in each of these cases, what we get is that this implies that y is less than or equal to x squared. And this implies that y is less than, which is the same as less than or equal to x squared. Okay, so conclusion, based on this wacky random variable that I defined, we get that y is less than or equal to x squared. That's going to be important for us because one of those properties of expected value, if I can just go up and show you, is this one. If you can have an inequality relating two random variables, the expected values are the same. So what we can say now is since y is less than or equal to x squared, we must have that the expected value of y has to also be less than or equal to the expected value of x squared. Okay? Now, we also have that y is discrete. Doesn't matter whether x is or not, y is clearly discrete. It only takes on two possible values, either 0 or epsilon squared. So we can calculate the expected value of y. I'm going to add a new page, so just give me just a second. So the expected value of y, I'll just make a note here. That's essentially, the sum over all possible y of y times the probability that y is equal to y. But y can only take on two possible values, right? So it's 0 if who cares? And it's epsilon squared if what? If the absolute value of x is greater than epsilon. So this is the probability that the absolute value of x is greater than epsilon. But that's interesting. Isn't that exactly what we wanted? Okay, so we get that epsilon squared times the probability that the absolute value of x is bigger than epsilon. That has to be less than or equal to the expected value of x squared. But all we can do now is divide both sides by epsilon squared, and we get our inequality. So we get that the probability that the absolute value, or the magnitude of x exceeds epsilon, that is going to be less than or equal to 1 over epsilon squared times the expected value of x squared. And this is Chebyshev's inequality. There's a more general one called Markov's inequality, which you'll prove in the exercises. A couple of comments that I'd like to make about this. In general, think about all the different kinds of distributions. And I know that we haven't really talked about a lot of them, but we have, of course, the uniform distribution, and we have the Gaussian normal distribution. We have ones that are like curved. Out of all those distributions, if this inequality works for all of them, it's actually not very good in practice. And you'll actually you'll do an exercise where you compute this and show how bad the bound is. Like it's equivalent to me saying, oh, well, the probability of this occurring is actually less than or equal to 1. That doesn't help at all. Like, of course it's less than or equal to 1. Yeah, it's not much better than that. But this is used for a lot of theoretical results, and that's Chebyshev's inequality. So next time we're actually going to talk about a couple of properties of variance, and that's all going to build up to the last thing that I want to talk about, which is the correlation coefficient, and we'll talk a little bit about linear regression. So hope to see you there, and thanks so much for watching.